In the past few videos, we've learned how to take the derivative of a trig function. We've learned how to take the derivative of a polynomial x to the n, and we've learned how to take the derivative of a natural log or exponential growth or decay e to the x or e to the negative x. Now we can look at each of these terms individually and add or subtract them from each other using derivative rules. Meaning, if I have a function that is a combination of multiple functions through addition or subtraction, I can solve for individual derivatives and then just combine at the end. Now, this might seem extremely straightforward, and it is, but we want to distinguish this from the multiplication and multiplication and division or quotient rules that we'll look at in future videos, which are not as straightforward. All right, so just a note on notation. If I write df dx or f prime, we mean the same thing. We mean the derivative of the function f with respect to x, or dg dx is equal to g prime, same thing, okay? And then we can write f double prime or g double prime for the second derivative, and we'll see that in some of the examples that we'll talk about in this video. So all that we're saying is, let's say I have a function y, it's a function of x, and it's made up of two individual functions, f of x and g of x. Now, if I could find the derivative of f of x on its own and the derivative of g of x on its own, then I could solve for y prime as just the sum of f prime and g prime. Similarly, for the subtractive derivative rules, if I know z of x is f of x minus g of x, then I can solve for each individually and just subtract those, the derivative of those, and that will give me my full z prime derivative. All right, so very straightforward, just understanding, taking the derivative of individual terms and adding or subtracting together. Make it very clear that this is only true for addition and subtraction. We'll look at how to approach if we have multiplication or division or quotients systems using multiplication, the product, or quotient rules for derivatives. So again, the past few videos we learned these derivatives, right? Here we have our trig derivative functions. Here we have our polynomial derivative. And here we have our natural log and natural number, e to the x, e to the negative x derivatives. Now, in red here, I have not mentioned the derivative of a constant or a constant multiplied by a function yet. So this is specifically for constant multiplied by a function. Anything other than a non-constant function multiplied by another function, we have to use a product rule that we'll look at in a future video. So I just want to fully flesh this out before jumping into our examples. So why is the derivative of a constant equal to 0? Remember what it means when we say that our function is a constant. It means y is equal to a certain value, like y is equal to 5. What would that look like on an xy graph? It would look like a horizontal line, right? At y equals 5, right? It would just be a horizontal line. So the derivative, remember, is just a question about what's the slope. What's the rise over run? There is no rise when we have a constant. So it's all run. There is 0 rise. So this will always be equal to 0. The slope is 0 when we have a horizontal line. Then we have a constant multiplied by a function, and we say that the derivative of this is equal to the constant multiplied by the derivative of that function, right? It's a pure multiplication piece. And I think you can easily see that with something like x, and then you put a constant in front of it, like 10x. So for x, the derivative using the polynomial rule would just be 1. 10 times x, you can see that the slope is increasing, right? You can visualize it if you graphed it. So at least for that one, it's very straightforward. Now, for something that's more complicated, when you put a constant in front of it, each derivative term is also increased because it's just rise over run. So it's the exact same concept. And that's why it can scale directly that way. So we will use some of these derivatives that we know on an individual basis to look at the first and second derivative using additive and subtractive rules. We'll do a number of examples to show you what that looks like, and we'll show you the graphs to kind of help you visualize what they represent. Okay, so I threw all the derivatives that we know on this left column so we can have something as a resource. All right, here is our additive derivative rule, right? The derivative of function f and derivative of function g can be individually solved for and then just add together. So my function here in this example is y is equal to function f, 5x squared, plus the function g, 2 cosine x. And so down here, I've drawn each of these individual terms. So in blue is 5x squared. In green is 2 cos x. So you see the effect of this 2 cosine x is mainly just in this small region here to kind of offset, not just with 2, right? That's why it's not just perfectly offset. It's offset, and then after you're some distance away from the 0 or the y-axis in either the negative or positive side, you're basically laying on top of the 5x squared. So how do we solve for this? All right, so first we want to look at this term here, 5x squared. So which derivatives would we use? Well, I can use this one, right? So the coefficient 5 times x squared. So I could take the derivative of x squared, just multiply that by 5. The derivative of x squared is going to be my polynomial here. So n is equal to 2. So n equal to 2. So 2 times x, 2 minus 1. So 2x. So 2x times 5. That'll be this term here. Then I have 2 cos x. Again, that'll be the constant 2 multiplied by the derivative of cos x. So 2 times derivative of cosine x is negative sine x. So we'll put that together. So we got 5 times 2x plus 2 times negative sine x. So just clean that up. I got 10x minus 2 sine x. And so my graph here, there's my minus 2 sine x in green. And then I have, it's a bit hard to see, but you have 10x in blue lines along here. Now these lines kind of crisscross from each other. This is not the best graph, but you know that they're going to crisscross at the different 0 points in this for this sine curve here. All right, so let's take an additional derivative. When we take an additional derivative, I can write this as y double prime, right, 2 primes. Or I can write as d squared y over dx squared, meaning second derivative. So again, I'll look at this term here, 10 times x. So the function x is a polynomial with n equals 1. So that's going to be 1 times x, 1 minus 1. So that's just going to be 1, the constant 1, times 10, minus 2 sine x. So minus 2 times sine x, derivative of sine x. Derivative of sine x is just cosine x. So I get 10 times 1, or just 10, minus 2 times derivative of sine x, which is just cosine x. And so I have minus 2 cos x right here in green. And then in blue, I have the constant 10. And then when you add them together, it's just going to be offset, right? So hopefully that's clear. This constant multiplied by a derivative form shows up over and over. So that's why this one is also very important. Let's take a look at another example. Let's take a look at a subtractive example. All right, here is our subtractive example. We have 7x in blue, this linear line right here. I have 2e to the x in green, shown here. And if I subtract these functions, we can see that we would have a 0 point when they cross here and a 0 point when they cross right there. Okay, So now if I want to take the derivative of this, I could take the derivative of 7x and then separately take the derivative of 2 to the 2 times e to the x. So 7x, this looks similar to one that we did earlier. This would just be 7. 2ex, if we look at our e to x derivative, it's just e to x. So this will also just be 2ex. Right, so 7 minus 2ex. If I graph this, I get my constant 7 in this dashed blue line here. I have e to the x in green. Since I'm subtracting from it, it flips it, and it uses the 7 as my asymptote. You can think of it as an asymptote, or you can think of it as an offset. If it wasn't there, it would be down here at the 0, and then dropping down. Right? Take the second derivative. Now we have a constant. Take a derivative of a constant is just going to be equal to 0, as we mentioned earlier. Take the derivative of 2ex is going to be 2ex again. So it's just going to be minus 2ex. Right? And so then, like I said earlier, here we have 2ex, the exponential growth, and then put a subtract it, or put a negative sign in front of it, and then we'll have it just flipped across the x-axis. All right, so this is 2 terms. We can add more terms. So let's do a couple examples with 3 terms. And you'll see it's not any harder. We just look at individual components. Now, the analysis you do with the combined form, that's an additional piece. But the mathematics of this, we're just looking at individual. So if you give me 10 terms added or subtracted from each other, as long as I have them in some rules that I can apply here, I can solve them if you give me enough time, right? So let's take a look at 3 terms. All right, so I have additive and I have a subtractive form. Now what you'll see, like hopefully you'll recognize, is additive and subtractive rules are basically the same thing, right? So you can visualize everything as additive, and if there's ever a subtraction sign, you can just treat it as plus -5. And then that's just a constant. The constant just changes to a -5 instead of just a +5. That's all it is. So essentially it's the same thing, but we'll just look at this for the sake of the introduction video as 2 separate pieces. So I have x squared in blue here. I've only shown the positive x-axis of this because I have my natural log term that only has positive x components here. So 2 ln x, natural log x, shown in green here, and then 5 in this black horizontal line, and the combination of all of these in red shown here, right? And it makes sense why it's combined the way it is, right? Initially, natural log of x dominates the effects. And then soon after, it basically has very little effect, and your total y value basically looks like x squared. That makes sense. All right, take the derivative of this. X squared, we know that one. We've done it before. That's just going to be 2 times x, 2 minus 1, so just 2x. 2 times natural log x, that's going to be a constant 2 times the derivative of natural log x. And where do we have it? Right here. All right, so it's going to be 2 times 1 over x, or 2 over x, minus the function 5, well, or the constant 5, right? So it's a constant. So we'll just say that derivative is equal to 0. All right, so then we have 2x plus 2 over x as my function. So let's graph that. We don't need to include this term here. So 2x, we have this blue linear line here. 2 over x, we have as this green line with an asymptote going to 0 as x keeps increasing. So again, initially, 2 over x has a strong influence on this system, and then soon after, right, very small values already, it starts reflecting the 2x term is going to dominate. All right, take the derivative one more time. What do we get? 2 times x, so constant times the derivative of x will just be 1, so 2, plus 2 over x. How do we treat x in the denominator? Well, you can look at this as x, or 1 over x, or you can look at this as x to the -1 power. So it's a polynomial in that case. So we got -1 times x to -1 minus 1. So x to -2, or x squared term, right? So 2 times 1 gives me 2, plus 2 times the end value here was -1, right? So -1, so that's where this negative sign comes from, this -1 term. And then -1 minus 1, so that's where the x to -2 or 1 over x squared term comes from, right? So we got 2 plus or 2 minus 2 over x squared. If we graph that, the horizontal line here represents my constant 2 function. -2 over x squared is represented here. And adding those two functions together, we get a graph that's asymptoting to y equals 2. All right, let's do one more example with 3 terms again. All right, this is the first time we see a square root term. So we have 4 square root x, and that's shown in blue here. Again, I'm only graphing from positive x values because I want only real numbers, and this will give me an imaginary number if I have a negative x value. I have 2 times each of the negative x, my decay term right here, right? So if we went to the negative side, it would drop from infinity down, and it's decaying. And then minus sine x. So I'm graphing positive sine x right here. So I'm treating this as additive and then subtractive. But again, I could have graphed negative sine x and treated it all as 3 additive terms. Okay, and then the combination of everything is shown in red here. So you see the oscillation due to the sine x continuing basically across this square root x term here. All right, so how do we take the derivative of this? 4 times square root x. I don't have a square root x showing up here, but I can look at this polynomial and treat it the same way. Square root of x can also be looked at as x to the power 0.5 or 1/2. So n could be my 1/2. So this could be 1/2 times x 1/2 minus 1. What's 1/2 minus 1? That's just going to be negative 1/2, or 1 over square root x. So 4 times 1/2 divided by square root x will be this derivative term, plus 2 each of negative x. Each of the negative x, I have that derivative, negative each of negative x. So this term will be 2 times negative each of negative x. And then sine x. Sine x, the derivative is just cosine x. Okay, so my derivative is 4 times 1/2 x to the negative 1/2. That's for the polynomial form of square root x, plus 2 times each of negative x, or 2 times negative each of negative x. That's the derivative of each of negative x, like we said. And then derivative of sine x is just cosine x. So we can clean that up, and then we'll get our blue graph, 2 over square root x. Green graph, -2 each of the negative x, asymptoting, right? And just flipping across the x-axis. And then positive cosine x, shown in black here. And in combination of that, you see the dominance of square root x term, or 1 over square root x term initially. That's reflecting that. And then you see the dominance of our cosine x term after that. Beyond that, the exponential decay term is already basically 0, and so it doesn't really have a major effect. All right, then we take the second derivative, 2 over square root x. Well, you can look at this square root x again, this 1 over square root x term, as a polynomial with x to the negative 1/2, right? So the negative makes it 1 over value. So then negative 1/2 times x to the negative 1/2 minus 1, or negative 3/2, right? So we got that term. Minus 2 each of negative x, right? We treat -2 as the constant. Each of negative x will be negative each of negative x. and then minus cosine x. So cosine x derivative of that is just negative sine x. So we'll have negative 1/4 x to the negative 3/2 plus 2 times e to the negative x minus negative sine x, or you could think of this as plus sine x, but I graphed it as a separate piece. So here we have 2e to the negative x. Here we have negative 1/4 x to the negative 3/2 in blue here. And then in black, I have negative sine x, so I'm going to subtract that out, right? That's why this oscillation and the total sum oscillation in red here are mirrored from each other, right? Because I treated this as a subtractive term. So hopefully that makes sense. Now we have a whole set of tools here. We can combine them in different ways. We can multiply them by a positive or negative constant in front. And now our toolbox, we can see, can solve many, many different equations. There is still a limitation, right? If I have anything that's a combination, like a x times sine x, I can't solve it with these tools yet. So the next couple of videos, we'll look at the product rule and we'll look at the quotient rule that will greatly expand our ability to solve more of these derivatives.